Hello and welcome back everybody to our March session of the Cells to Galaxy speaker series. I'm Jeff Pixon from the National Radio Astronomy Observatory, which is an FFRDC of the National Science Foundation. As usual, our meeting is being recorded and will be available for viewing on the main Cells to Galaxy's website on the speaker series program page, and the link is in the upper right corner of the registration page. Attendees cannot be seen or identified in the recording, and we'll also provide that link in the Zoom chat box during our meeting today. During our discussion, please feel free to use the Q&A box in your Zoom for any questions you may have. And additionally, you can also use the Slack workspace both during the session and after today's topics have been covered. So for today's topic, we'll be identifying areas of collaboration. We have four subjects to present today. The first will be a brief panel discussion about the lessons learned from the presenters that we've had over the past several months. The second will be a discussion about our in-person workshop that's coming up in June. And the third topic will be some grant examples that teams that if they want to form can go after. And then the fourth topic will be going over a couple of demonstrations from both the medical imaging side and the radio astronomy side. So without further ado, we'll hand it off to Dr. Neb Durek. Take it away, Neb.
Thanks, Jeff. Hi, everyone. I wanted to start things off by talking sort of in general terms what I got out of the various talks that we've heard during this series. And first by pointing out some similarities between astronomy and medical imaging. As we've seen from the various presenters, astronomy and medical imaging really share pretty much the entire electromagnetic spectrum, and that's that's indicative of the potential for collaboration just on that basis alone. We've seen, for example, that MRI and radio astronomy share the radio frequency part of the spectrum. Computed tomography and X-ray astronomy share their space, as does, for example, PET imaging, positron emission tomography versus gamma ray astronomy. And of course, they both are solving inverse problems. However, there hasn't been traditionally very much collaboration between the two fields for two particular reasons that I'd like to point out. One is that in medicine, we use probing signals to actually illuminate an object and gather data from it to figure out what the inside of the object looks like. And that really lends itself to the technique of tomography, which is not a particular strength of astronomy. And it's also near field imaging versus far field imaging for astronomy. So there are these fundamental differences that sort of kept the two groups apart. But I think enough similarities have been identified during these presentations that, for example, reliance on Fourier transforms or similar transforms, that we can start thinking about how to identify more specific areas where collaboration is truly possible. So where we see the next step in terms of where we're going with, for example, the in-person workshop and so on, is to figure out what the similarities are. For example, both fields use, to a large extent, K-space as raw data. We start off with that, and then we use various reconstruction techniques to get us into the imaging domain. And so there's great potential there for overlap in terms of how we actually do that, how we go from raw data to images. There's, of course, the whole idea of visualization. How do you take multi-axial data, multi-dimensional data, and visualize it effectively for human interpretation? How do you handle large data, both from a visualization perspective as well as from a data mining perspective? And that's where AI and machine learning come in. And I think there's great potential there for the two groups to learn from each other. And so finally, I think from my perspective, where I see the in-person workshop going is really to identify, based on these areas of overlap, specific scientific problems that can benefit from these overlap of interests. And as was mentioned by Jeff, ultimately, of course, a true collaboration requires funding. And we've identified some initial funding sources that we're going to talk about that could not only initiate a collaboration, but keep it growing. So with that, I'll pass things on to Sanjay so he can give his impressions.
Thanks, Neb. Thanks for a very good introduction. I think I'll have only a few things to add to what Neb has already described as similarities and differences. One thing is I'm a radio astronomer by profession, and sort of on and off have read about particularly medical MRI imaging. But via these series, I learned something, a couple of things that actually I did not know or I had misunderstanding of. And some of them are fundamental. It was very exciting to learn that that's how it is done. One of them being the way data is collected in the two domains. While the data is collected and mathematically it can be described once collected, it's in the K space or in the Fourier domain, and therefore Fourier transform, which is the linear transform, you can take it to imaging domain. But it was fascinating to learn, at least for me, and I hope this understanding is right. I'll have it reviewed by medical experts later, that MRI imaging, for example, does not have a limit on resolution or the larger scale that they can sample. It's completely controlled by the magnetic field gradients that they have control on, quote unquote. Whereas in radio astronomy, we have very hard limits on the larger scale that we can measure and the finite resolution that our telescopes give. That leads to quite a bit of overlap as well as differences, so which is why both fields have evolved differently and therefore potential for crossover and using techniques from one to the other. The other thing I noticed, my mind noticed throughout the series was that this series was mostly focused on imaging and very little talk about calibration, which is, as any radio astronomer would know, in radio astronomy is a very important part. Calibration is almost not a separate thing that can be done separately and imaging separately. With the current sensitivities of radio telescopes, they are very mathematically as well as in practice quite intertwined. And therefore the calibration algorithms that radio astronomy field has developed are actually quite advanced, and some of them I feel can be applicable in the radio astronomy, in the medical imaging field. The other point which Neb certainly hinted upon is the visualization. So once you can do all your calibration and imaging and finally comes an image, those images at this point are at least three-dimensional, or if not four-dimensional. We have even polarization in addition to frequency axis. And visualization of that, they are, in terms of databases, they are very large at this point, running into almost a terabyte right now and probably going into many terabytes very soon. Mining the information, scientific information out of it, it is not possible to just look at the screen and figure out for a human. So potential for AI kind of machine learning algorithms, AI algorithms, which are sort of making their way in radio astronomy, but not in a regular way. These are the fields, I think, and of course, handling of very large data sets running into hundreds of terabytes very soon. So high performance computing kind of applications in both fields, I think, are very fertile ground for collaborations, and I look forward to our in-person meeting to figure out some of these areas where we can apply the techniques from one to the other. That's about all I will have. I have many more thoughts, but I don't think we'll have time for all that, and that's why the in-person meeting, I guess. With that, I'll hand it over to Greg for his thoughts on what he felt of the series.
Thank you. One of the things that impressed me most about this series of discussions that we've had is that there's so many similarities in how we do things and what we do. And one of the things that I was particularly impressed with is data management styles and data processing. There are a lot of tools that are used in both radio astronomy and medical imaging for things like image processing, data extraction, data understanding, and data transmission. One of the things I was most impressed about was the distributed processing capabilities that radio astronomy has started to use, or has been using for quite some time, because one of the things that they have an advantage over that we don't really have in medical imaging is that we've got personally identifiable information and personal healthcare information by definition embedded in these images, whereas the galaxies and other astronomical observations are not necessarily a PII. So that stops us, but that shouldn't stop us from finding a way to do larger scale processing. And this is one of the things I'm looking forward to exploring further in our workshop, is how can we do such things on the large? As Sanjay had mentioned, data sets are huge in astronomy, but we're starting to get much larger data sets in medical imaging now, and learning how to deal with those large sets of raw data that we need to do to process into, say, whole body PET CT images. We're going to have to learn from this, and I think that we have that opportunity to do also. So, in general, I'd say we have a lot more in common than we have different, and that there's a lot that we're learning from each other. I'll pass this on now to Prasant.
Yeah, I'm going to echo some of the sentiments that the other speakers other panelists have raised. So, but a couple of things that really stood out for me is that the devil's definitely in the details, and the details can't be glossed over. So a couple of points to make is, for example, when you're dealing with humans, you have to worry about whether they're going to wiggle, they're going to move. You cannot arbitrarily raise your magnetic fields. So these actually do place some sort of sensible constraints on what you can do with an MRI too. So which is very interesting. So the limitations though might not be mathematical, but they are actually physical and more biological than one would think about in radio, which is very interesting. So the near field versus far field is also an interesting shift, but it also means that the way you approach optics is slightly inverted, which is kind of nice. It's a little different to think about. Things that you take. Far field in radio astronomy is beyond the moon. So if anything that's shorter than the distance from the Earth to the moon is near field, and for a radio telescope. So and strangely we rarely look at that. So which means that the way MRI approaches their data is a very different and unique perspective. So all the effects that we typically tend to throw away as being, it's on a 2D plane, it's no longer on a 2D plane. And those make for some excellent oddities. If you are in doubt, go check out Dan Sodexon's talk. He laid it out very, very well. The cross comparison over there was excellent. I also found that the first initial set of introduction talks were brilliant. And actually I felt like you're taking a beginner's intro into MRI imaging, at least for the likes of me, which is extremely fascinating. That's what I have for now. I think I'll hand it over to Nicole.
Great, thanks, Prashant. So I'm Nicole Cyberlick, and I am an MRI physicist in the radiology department at the University of Michigan. And so, I really have to echo Prashant that I really loved the introductory lectures. These were the ones that allowed me to, understand how our two fields could potentially mesh. And I think, from there we moved into some really exciting application talks. And I love learning about those applications, but I have a really difficult time actually delving into how our two fields could fit together when we get very specific into the applications, because I just want to, get the very basic details of how we're dealing with our data and the algorithms. So, as an MRI physicist, what I think about a lot is how we can deal with the constraints of our MRI data collection, how we could maybe make up from some of the data that we can't collect, what other sources of information do we have? And, while I feel like I know that very well in medical imaging, I won't maybe feel like I really understand the actual ins and the outs and the problems that are faced in radio astronomy until I really get into the data. I have a data set and I can look at the algorithms, look at the code, and that will help me understand where the actual similarities and differences are. And I can't remember who said it, maybe Greg, that the devil is in the details, right? It's really those specific processing algorithms that have to do with one field or the other that we really have to understand, because maybe there's a great solution in one of our fields that could be easy to implement in the other if we just understood exactly what those corollaries between our different kinds of data and algorithms actually are. And so I feel like, what I want to see is a data set, and step by step how we process it and look at the intermediate products of that processing and understand why that's done, and to see how our two fields are really similar in both the big picture, which we've already seen, and then also the specifics, those little processing bits. And I think only that way we'll actually really understand whether the knowledge that one group has could be successfully transitioned to the other group, or potentially even used to build something that goes beyond each of our individual communities. And so I think we started scratching the surface there, but I think now I want to take that next step, now that I understand, the very, very basics and maybe where we're going with some of the techniques, but to really say, okay, let's get our hands dirty and dig in. And I really need I've been saying the kindergarten class where, there's the teacher who is explaining what's going on, but I can also, have my own MATLAB or my own, whatever platform we're working with, and my own data set, and I can start messing it up and then asking questions of the kindergarten teacher to say, okay, what did I do wrong here? What am I missing, to really understand the ins and the outs. So, kind of now to take this particular seminar into a transition, we are gearing up for our big in-person meeting. So it was always our goal to start with the seminar series, especially due to the constraints that we had because of COVID. And we were always going to culminate this webinar series with an in-person meeting. And so I want to remind you all to mark your calendars that our in-person meeting is going to be held in St. Paul, Minnesota, from June 22nd to the 24th. And the plan that we've developed for this 3-day meeting is based on the impressions that this group got from our webinar series, and then also the feedback that we got from you as our community. And so, what we would like to do in this 3-day meeting is to really meet these open needs. So to, really get our hands dirty, dig into each other's data, and then try to find actual specific collaboration projects that we can all work on together. So we've made a plan, and so our in-person meeting is 3 days, and on day 1, we're going to be diving into data from each of our communities. So from the medical imaging community and the radio astronomy community. So if we use medical imaging as an example, the participants might get some MRI data and some basic code. Maybe we'll look at CT, the different modalities that we have. And then the instructors will offer tutorials to describe exactly what the data are, how they're processed, what sort of simple reconstruction tools we use. And we'll do, of course, the same thing for radio astronomy. So we can really, again, take a look at each other's data and processing tools to dig into it. And then on the second day, we're going to take a look at some of the problems that are proposed by participants like you, and work on building teams around these big problems in medical imaging or radio astronomy or even beyond, with the specific goal of writing grant proposals, which bring expertise from both the medical imaging and radio astronomy specialists together in a unique way, right? Only if we have a group like this can we actually bring that together. And, I think me personally, an in-person meeting is really essential for that, because that's how we'll be able to actually meet each other and talk about our problems and really workshop how we could potentially solve them. And then on the third day, we're going to wrap up with project proposals and to see what might be feasible to actually write a grant on. And so, in the interest of writing an actual grant, we do have a funding mechanism or two in mind for some of these proposals. And in order to discuss what that is, I'm going to hand over to Jeff to get an idea of what one of these potential proposals could look like.
Thank you, Nicole. And I'm going to share my screen real quick. to illustrate one of these programs. So this is the National Science Foundation Convergence Accelerator Program. It's specifically designed for multidiscipline teams solving a problem in society. And the way the program works is it's kind of a 2-year process where they go through an ideation where they want the scientists, researchers to kind of tell NSF what the problems that should be solved. They have a workshop, and then they go into further development of those topics. And then they actually, after they finish that process, then they put out a solicitation for proposals. And it's 2 phases. The first phase is to basically identify how you would solve a problem. And then the second phase is actually go and do some of that work for 2 years. So it's almost a $6 million grant in total when you get to the finish line. And this is kind of fits perfectly in with the kind of the cells to galaxies ideas, because we're mixing disciplines, scientific disciplines and activities from a lot of different areas, not just from radio astronomy and medical imaging, but there's also opportunities for machine learning and things of that nature. There's also programs that will, and part of what we want to do at the face-to-face meeting is to come up with teams who are interested in proposing to these, and then following it through the process, and then completing the work. There's also opportunities with the National Institutes of Health, and Dr. Greg Cohen can give us a little bit more information about that. So I'll hand it off to him.
And yes, there are several different areas in which the NIH is funding research at this point in time. Most of it is focused upon things like physical sciences being applied to things like oncology problems and those kinds of things. We do also have some grants that are being funded by National Institutes of Biomedical Engineering and Biosciences. And NIBIB is also focusing on a collaboration between medical imaging and physical sciences. And so some of these opportunities are out there. There are always a new flux of opportunities. And one of the things that I would like to do is to put up a link on our website pointing to some of those funding opportunities. And at our in-person meeting, I'd like to have some more opportunities actually focused down on that, perhaps as we get together and we define problems to solve, that these funding mechanisms may be useful to us to help go out and solve some of these problems.
All right, and so we'll wrap up today's session with a couple of demos from both sides of the aisle. Get off with Nicole, and she's going to take us through a demonstration of some medical imaging algorithms and software, and then we'll move over to Prashant.
Great, thank you so much, Jeff. So before we get started with the demo, I first want to just remind everyone that if you have any questions about the format of the in-person meeting or what we might be doing, please put them into the chat. We can take those if you have any. And I just want to also, kind of double down on what Jeff was saying before, that we're going to be looking for some of these big questions, the big problems that we're facing either in medical imaging or in radio astronomy. We're going to be asking you to help us figure out what those should be. So these are going to be the problems that we highlight at the in-person meeting. So watch your inboxes for a call for proposals, or like it's like a call for abstracts for a meeting, except instead of being a scientific abstract, it'll be a call for a big question. So that's going to be coming very soon. So of course, as we just mentioned in the in-person meeting, before we do those deep dives into the big questions, the big problems on days 2 and 3, day 1 will be these kind of demo workshops looking at data. And so what I'm going to do right now is to just kind of scratch the very tip of the surface of the kinds of things that we might be looking at when it comes to medical imaging data. So I'm going to try to share my desktop, which I think is the easiest way to do this. And you should be seeing right now my MATLAB, which is where I do most of my, my medical imaging work. So if you can't see it, somebody please shout out. And I'm going to ask for help from my panel. If there are any questions about what I'm doing or what I'm showing, please ask them in the chat. And if there are any questions, please from the panel, shout them out to me because I can't look at the chat while I'm doing the demo. It's just too many windows. Okay, so, oh, yes.
Oh, no, I said got it, yeah.
Okay, perfect.
I got questions for you, don't worry.
Got it, awesome. Okay, so so what I'm doing here in MATLAB is I just have a basic script where the code is meant to be very big, and I'm just gonna run it section by section and explain what the code is doing and then what we're going to be looking at. So the first thing I'm gonna do is load in this, this little map file, which has some MRI data in it. So hopefully it ran. Okay, I just loaded it in. You can see here in my workspace, I have this variable KSP. This is MRI case-based data. So this is what was actually collected by the MRI scanner. It's a three-dimensional data set where the sizes are 192 by 192 by 192. So this is 3D case-based data. It's complex data. All of our case-based data is complex. And again, this is actually what we collected from the MRI scanner. It had a format that was proprietary. We had to figure out how to read that in, but this is the kind of data that we would be giving to you as part of the workshop. I'm also going to mention at this point that this data was collected by one receiver coil. So there's actually another dimension in here that's by one, because I've only used one coil to collect this data to make things easier. Typically, we would have a fourth dimension, which would be number of receiver coils, which makes the whole processing a little bit more complicated. But just to keep it simple, we just have this single dimension for our receiver coils. Okay, so what is this case-based data? So what we typically do, because we can control how we sample the data in MRI, we collected this data one line at a time. So we collected 192 complex points, and then we repeated that process 192 by 192 times in order to fill up this whole three-dimensional matrix. So in this little section of the code, what I'm going to do is I'm going to plot one of these lines, so just one line of data that we collected, and I'm going to cycle through 192 different lines so you can kind of see what these different lines of case space will look like. Here I have the absolute value because, again, the data are complex, so I'm just plotting the absolute value here. So hopefully when I run this, you guys should see popping up on the screen, which is hopefully happening, these different lines of case space that I've collected. So you can see that this is the Fourier domain, so they're kind of nonsensical. There's going to come a time where we go through the center of case space where we have a very large peak in our data that we've collected. This is, essentially it's difficult to see what's going on here because it's just a whole bunch of numbers in our Fourier domain. One thing that I did want to do is show you, let's look at the max of the absolute value of this case space to get an idea of the dynamic range. So our maximum value is about it's 193 units. There isn't really a nice set of units that we can use for case-based data. It's all kind of relative. But if we look at the minimum value here, just get an idea of the dynamic range, we see that it's pretty tiny. So we have, about 7 orders of magnitude difference between our highest point in case-based and our lowest point, which is something that we can see from our data. Of course, I said before that this data is complex. So I'm now just going to show you the plots of the real and imaginary values. We could look at, magnitude and phase. We don't do that often in case-based. I can run that here for you. And again, it's going to be a little bit boring because they're just kind of numbers here in case-based. But you can see that we have, both sets, or we have this complex data that we're having to work with. I'm actually going to skip this line where we have a common axis because we don't usually look at our case-based data one line at a time. It's kind of a funny way for MRI people to look at it because this is trying to encode something that's in 3 dimensions. And so we try to look at it as almost like, a 2-dimensional image where we could look through all 3 directions. But I'm just going to show you what case-based looks like if we, instead of doing a plot of a single line, we make an image of 2 directions, 2 dimensions at once. So that's what I'm doing here. I just have, 2 directions where I've selected one of these kind of planes through my 3-dimensional case-based to look at. And it looks something like this, where here we have this peak in the very center of our case-based. Our data or our images don't tend to be particularly sparse. So in K-space, they are actually very, very sparse because we have most of the energy concentrated here at the center. It's kind of hard to look at it when we have this huge dynamic range. So often what we do when we're plotting our K-space data is just to scale it, by some value or take the log of the data. I'm just going to show you what that looks like. So this is kind of a scaled K-space. So again, we have this point here at the center, which is containing most of the information about the contrast of the object that we're looking at. And then, all of these values here are very low, but they're really important because they're providing us the resolution in our images. And I would say MRI people who are working on, algorithms and image reconstruction, we look at K-space a lot to see, if there's anything funny happening in our data collection, which would cause artifacts in our images. And this is typically what we're going to be collecting and then looking at. Okay, so K-space is fine, it's how we collected our data, but let's actually make an image. And this is a really simple K-space where, we don't really have to do anything magical to it to make an image. It's a three-dimensional K-space, so we take a three-dimensional Fourier transform to convert it from the time domain where we collect it into the frequency domain, which is the image that we're going to be looking at. So here's our three-dimensional Fourier transform. And then I'm just going to plot basically we have three-dimensional K-space, so we have a three-dimensional image, and I'm just going to plot a slice through our three-dimensional image so you can kind of get an idea of what we're looking at. So I have the Fourier transform, and here is my image. It's hard to see because MATLAB plots things in jet. We'll actually look at it in a grayscale in a second. But this is just what's known as a resolution phantom, where we have, it's a bottle of water with a whole bunch of little vials with different properties, magnetic properties in those vials, so we can get an idea of the resolution and the contrast that we're getting in our image. Okay, so this one image is a little bit boring. So what I'm going to do is just cycle through a whole bunch of these images from the top to the bottom. Here I'm using a gray color map, so it's a little bit easier to see. And we're just going to stop and look at each one as we're moving through this three-dimensional image. So here we go. We're starting outside the image. It's just noise. This is just air. Here you can see where we're moving into this phantom, our bottle of water, where it has those different vials and different little features, so we can check out the resolution that we're getting in our object. So what's the finest feature that we can make out given the K-space data that we've collected. And this phantom is nice and easy to scan because it's not alive. It's not moving. We can scan it for as long as we want. And it doesn't have some of the bells and whistles that in vivo scanning does, but for this demo, that's perfectly okay. And of course, this is a three-dimensional image. So what I'm going to do is, instead of going from top to bottom, I'm just going to go from left to right now through the image. It's a three-dimensional K-space, three-dimensional object as well. So that's what this guy looks like now, coming at it from a different angle, where you can see that it's kind of a ball shaped with two flat ends, and that's just the resolution phantom that we use. While we collected a three-dimensional data set for this phantom, so we could see what's going on in all of the different parts of it, we usually would not collect a three-dimensional data set in a person, because you can imagine if you have to collect one line of data 192 times 192 times, it's going to take a pretty long time, especially if it takes us a long time to collect each line. And so we typically don't collect three-dimensional data sets in vivo in people, just because it simply takes too long. But for something that's static, like this phantom, this is pretty easy for us to do. I see some questions in the chat. Yeah, this is okay. This is a K volume. Yeah, that is true. Hopefully it's clear now. Okay. Trying to hold on. Close my chat so I can see my screen again. Okay, here we go. So as I mentioned before, one thing that, if we're collecting this volume of K-space data, this is going to take us a really long time to collect. And so what we often do is skip lines of data. We just don't collect them. And the way that we mimic that when we're doing our reconstructions, sometimes we want to collect the whole volume so that we have that as our ground truth, but we want to pretend like we didn't actually collect all that data. And the easy way to do that is just to like set every other line in our data set to 0. So what I've done here is I've taken my k-space data and I've copied it into another variable, and I've set every second line to 0. So basically, I just didn't collect it, is what I'm doing. And if I just, take my k-space, then where I've zeroed out every line, I'm just going to plot it or make an image of it to show you what that looks like. So you can see I did indeed skip every other line of my k-space data. It's just going to be 0 as I'm going through it. Okay, so now my scan would be twice as fast, which is good. But I'm going to have a problem with my image because I've skipped every other line of k-space. So in order to show you what that image would look like, I'm simply, again, taking the 3-dimensional Fourier transform of this volume of k-space data, and I'm going to plot one of the sections from the center of that image. Here we go.
So Nicole, there's a question asking
okay.
what is the median value in this k-space sort of look like, median or mean? Because they raise the point that you showed the max and the min, so then they want to know what a representative number looks like.
Yeah, I'm not sure. I mean, we don't usually look at that. I can calculate it. But I don't know if it's really, I don't know if mean is even the right. Let's find out.
Yeah,
okay.
Plus
the mean value. The median will be something totally different because there's so few values, pixel value or k-space values that have such a high number. Most of them are going to be really, really tiny. Median is what, oh, there we go. There's median.
So median gives you an idea of the noise, basically, that you have.
Yeah, it's like an RMS.
RMS, yeah.
Okay, we never do that in looking at MRI data. So if we want to calculate, actually, let me pull up.
Your radio astronomers talk of noise a lot.
We do too, but we calculate it never from our k-space data. So I'm just going to plop this guy here and go through 97. That one because I don't know where the window is. Okay, so it's easier actually to quantify using when we have one receiver coil, but often to quantify to measure the noise, we would look at the signal over some sort of constant area, and then look at the standard deviation of something in the air where there shouldn't be any signal, and use that to calculate an SNR. That doesn't work very well when you don't have, an area where you should have a constant signal, which is basically anywhere in vivo. And anytime you do any sort of advanced signal processing algorithm on your data, then you aren't going to be able to get a really good measurement of your SNR either that way. Sometimes to us, SNR is important, and sometimes it's the CNR, the contrast to noise. So whether you can tell the difference between this file and this file, for instance, but we almost never look at the actual levels of signal and noise in k-space. It may be something that we could do, but this is not how we do it right now. Okay, it says, I downsampled by a factor of 2 in k-space and I reconstructed. So a low pass filter, so a low pass filter over my k-space data would still lead to aliasing artifacts, but I just wouldn't have the resolution that I had before. So basically the low pass filter in k-space would be equivalent to keeping the center of k-space and getting rid of all the outside. But that isn't going to affect this isn't going to change the fact that I just haven't met the Nyquist criterion in that direction. And that's what's leading to those aliasing artifacts. It has nothing to do with low pass or high pass filtering. I could try to do some, this is how a lot of our parallel imaging algorithms work. They use information from other sorts of spatial sources to get that information back, but a low pass filter wouldn't help me in this, to recover that information in this demo. And actually,
so Nicole, there's another question from
yes.
from Christina asking. So what kind of formats are MRI data stored in? Are any specialized MATLAB toolboxes needed to load / process these things?
That's a really good question. So each MRI vendor has a slightly different format, and it's a proprietary format. So those vendors, weirdly, they don't like us to be using MATLAB for reconstruction processing. They want us to be using their code, their software. It's way too complicated to try to learn all of that. And so basically every MRI lab has learned how to crack the, the proprietary data formats and convert them into MATLAB. We understand that that's really not the best way to do it. And so most of the vendors now allow us to convert data into what's called an ISMRM raw data format. The ISMRM is the International Society for Magnetic Resonance in Medicine. And so this is basically a common format that all of the vendors are kind of okay with, and we can convert data in that ISMRM raw data format into MATLAB. So there is no toolbox in MATLAB that will let you get that vendor supplied data and move it into MATLAB. We have to just know how to do that, and you have to get a code for that. The ISMRM raw data format, I believe, can be read directly into MATLAB, like it's maybe tab delineated or a semicolon or something, so that will actually put it in. Then the trick is to understand what the different dimensions are. So you might see something, depending on how the data are collected, like cardiac data has, yet another set of dimensions because you have to deal with different cardiac phases showing different heartbeats. And so it can be a little tricky sometimes to go in and figure out exactly what these different dimensions are. And I've kept it pretty simple here, but that would be a great example of something that we would show in the actual workshop, like what those different dimensions could be and how to actually deal with them. But definitely in the workshop, we would be looking at MATLAB data. Was there another question?
No, that's it. Awesome.
Okay, perfect. I'm just closing up with my fast images here, just so you can actually see the aliasing artifacts better. So what I'm doing is I took that data set where we left out every other line of K-space. So again, we haven't met the Nyquist criterion in one direction. And so the natural result of undersampling in the time domain is going to be, aliasing artifacts in the frequency domain, which you can see really nicely in MRI data. So this is what this will look like. So again, this is just running through the entire phantom from the bottom to the top. Again, we can clearly see aliasing. This is exactly what we're getting. So again, to that question that came up before, if we had applied a low pass filter to our MRI K-space data, we would still have this aliasing. We would just have lower resolution images then, which would be like doubly problematic because you might not be able to see small features and you'd have to contend with aliasing artifacts. The only way we can deal with that is either to collect those missing Fourier lines or to do more advanced reconstructions that use information from other sources about the spatial localization of some of these signals. And that's the kind of thing we'll talk about at the workshop. So with that, I'm happy to take any more questions in the chat if they're floating around about MRI data or how we do, deal with medical imaging data in general. But I'm going to pass back off to Prashant, who's going to be talking about radio astronomy data.
Hi, so I'm going to share my folder up. I'm hoping that you can see what I'm seeing. So typically in radio astronomy, we work with open source tools. So the stuff that I'm going to be showing to you is stuff that we generated, is a software package that we generated and use for radio interferometric data reduction in NRAO, which is basically CASA. So there are multiple ways that you can install CASA. So where you can get it, it's available for free. You can download it from CASA or nrao.edu. There are different ways to get it. You can either use it as an inline Python library, or you can use it as a standalone Python environment wherein you can run your data analysis tools and packages. So it gives you multiple options and different releases. We typically put out 2 releases a year. And I'm going to be talking largely about the imaging portions, and all the imaging help and everything that I'm going to be talking to you about is mentioned in extremely great detail up on this read the docs page for CASA. So you can find the documentation for all the software and all the tools that I'm going to be showing at casadocs.io. So, and in that subhead, I'm mostly going to be focusing on the synthesis imaging. So this is a lot of the stuff is what you saw in Urvashi's talks, these images, and how we actually go about making an image. Some of the so this simulation is what I'm going to be using to show you how we actually go from data to what's in the sky. All right, so we work on a basic format. The format in which our data is used and processed is called a measurement set. And a measurement set has a specific set of metadata, and so the metadata need to be filled. So this is a sample idea of how we fill the metadata. It includes telescope information, where are you located on the Earth, depending on where you're located, how the sky looks to you. Things like that. What kind of feeds are you using? So once you set up all your frequency information and what kind of time sampling that you want to set up, then you can actually simulate what the telescope would see in the sky. So I have a Python notebook here, which I will put up on the GitHub page. I will also throw it up on the Slack after we're done. I'm also going to be switching to the standalone CASA installation, because some of these things have locks, and if there is a lock that bothers me when I'm running it inside a Python notebook, I would actually have to restart the whole Python notebook, which I don't necessarily feel like doing at this point during this demo. So so even though there's code and there's text here, I'm actually going to be reverting to this monolithic installation periodically. All right, so Nicole showed you what a 2D version of medical imaging data looks like. This is a 2D slice of the sampling that we have from an interferometer of the object that I've simulated. In my case, it's a galaxy called Cygnus A. It's a very nice looking radio galaxy, of which we'll make an image of at the end. But each of these points here actually represents an individual baseline for a given time step and at a small narrowband frequency. So there are different axes in which you can grow the data, such as in the frequency domain. So the sampling I've kept is to a single channel. So in radio interferometer, so typically we channel roughly about 1,000 channels, or roughly a few gigahertz in bandwidth. And most of the simulation is going to be focused on L-band, which is basically from 1 to 2 gigahertz in frequency range. So the points that you see here is essentially what the instantaneous sampling looks like in the UV space for us. So if, like Nicole was showing, Fourier transform of this will get you to the sky. But in order to take this Fourier transform, we have to perform a few things. We have to do some massaging to the data, and I'll show you those steps. But what I wanted to point out is that we have a plotting tool here that actually allows you to pick different aspects of it, such as you can just plot what the amplitude looks like as a function of across the entire UV plane. And for example, it's quite simply will look like that. So so the units, sorry, I got the axis wrong. So I'll flip the axis. My bad. I want this to be amplitude and this to be UV. Yeah, I was looking at the data the other way. Come on, man. Oh. Sorry about that. So this is typically what you're sampling. So as Nicole was pointing out, as the faraway points, which actually have very little power in them, are actually contributing to your resolution. So the longer the baseline length, the smaller the resolution of the sky. So this is essentially what you're looking at. And as you go closer and closer towards the center, she showed that you in the UV sampling, you have a central peak. In our case, we missed the central location, but there's a little bit of interpolation and stuff that happens here when we actually try to make an image. And more on that if you go back and look at Urvashi's talk. So typically, okay, there's a question about what kind of radio frequency interference we encounter. So we see a lot of satellites. We also see stuff that's coming. We also see things like car remotes and stuff in S-band. It depends on which frequency band that you are working in. L-band, which is largely satellites. And a lot of this, and there's also some radar. So we actually throw out huge chunks of our of the band. So roughly, Damon, you end up throwing away nearly 40 to 50% of your data because it's unusable because of radio frequency interference, typically. So I hope that answers your question. So this is what it looks like. So you can also actually, of course, plot it as a function of spectrum, but since it's only a single channel, if I plot it, it'll just show up at a single location. So anyway, so here's a general plotter that you can use to actually step through different dimensions of the data and then see what it looks like. So our typical data set varies as a function of time, frequency, polarization, and so that's the stack. It's a 4-dimensional stack, and you can collapse in different axes to actually get at your data. We also have tools that will actually list out the metadata information that you have. So what I've essentially done is I've created an empty image. I've then put in this model that I want to simulate, and then I predicted it. So essentially, it's a simulation of this galaxy. So now the question is how do we image this back? So Nicole showed you that it's a quite simple question of taking a 2D FFT. And in order to take a 2D FFT, we run this task called clean, which is our process here. Sorry, I'm an Emacs guy, so bear with me. So we run what's called a standard hog bomb clean. We'll blow up all prior hog bomb set of info. So what this is going to perform currently is that it's going to take this UV data, it's going to put it on a regular grid, and then just take an FFT. And once it takes an FFT, it's going to pop up that image for us first before we do anything else. So the process I'm trying to do is called interactive cleaning, where we actually see what what our data looks like as we image it. So I'm sorry. So these are I've predefined the function and all the parameters that actually go in, so that makes our life simpler. So what this has done is it's essentially taken that 2D plane that I showed you, put it on a grid, and then performed a fast Fourier transform. So this is what it looks like. You can see these crazy artifacts that come around it. These are coming from the point spread function, because our sampling is extremely sparse in the UV space, as you saw. So we do this process of deconvolution where we actually remove this effect of this sparse sampling. And this is done using a simple steep gradient algorithm. And that's hence the name clean. So what we're going to do here is we're just suggesting to clean that it focuses its information on these parts.
Prashant, this is Sanjay.
But yeah.
I'll just add here that the reason why we do this deconvolution or the algorithm called clean is that in this initial image, which is Fourier transform of the data, the dynamic range is very 100 to 1. Whereas telescopes allow dynamic ranges of 3 or 4 or 5 orders of magnitude more than that. And the reason why we have to do this processing is to get to the dynamic range.
Yeah, no, absolutely. So the thing that I was trying to show here is that as we start cleaning deep, we'll start seeing fainter and fainter emission. So one particular thing I want to bring your attention to is this central source here. So this is basically a galaxy which has 2 giant radial lobes, but the center of the galaxy is here. And at the center of the galaxy doesn't show up initially. It only shows up as you progressively start cleaning down. So there's a dynamic range difference between these lobes, and the center is a few hundred to 1. At this point, it's a few hundred to 1, so that I can easily show you what it to get to an answer rather fast on my laptop. But a typical data set is a few hundred gigabytes, and the dynamic ranges that you can achieve exceed 10 to the 5. So for this particular data set, Neb was talking about, you can get up to even a few million. But that's not going to happen overnight. It's not going to happen in this talk right away. So here's a quick demo. What I'm asking Clean to do is what the Clean algorithm does is that it goes and locates all these the brightest brightest points, puts in the shape of the point spread function, and then subtracts it. I'm just going to let this run, and I'll show you what our typical point spread function looks like, which is just basically the Fourier transform of the sampling function. So, for example, here is the PSF. So the incomplete sampling leads us with a sampling function that looks like this. So every single point in your image is convolved by a point spread function that looks like this, and this has to be removed. And that is the process that was happening. That's the deconvolution that we were performing on the fly. It finally results in a residual and then an image that we have made. I'm going to show you what our cleaning residual looks like. You keep cleaning down until you hit what looks like a normal noise flow. This is not really at noise level, but we're approaching close enough to noise that it's hard to distinguish between peaks in the source and peaks in the noise. So this is roughly the place I've chosen to stop. So we also have different algorithms. So the thing that I wanted to point out is that we chose, in this case, to use a model that treats only point sources. So it picked all the brightest point sources it could find, and then it deconvolved sources from, it removed the point spread function from each of those locations. So for a nice galaxy, this is roughly the set of samplings that it found to reconstruct an image that actually looks like this. So that is what the actual galaxy looks like. You have the central core, and you have these two nice jets that go out at these two hotspots in the loops. We have different deconvolution techniques, and I just wanted to point out that there's another one called multi-scale, where we say that, hey, the source has very extended emission. So we want the models that we are using to make up this the source to be representative of what's actually in the sky. So you want it to be Gaussians, and that looks at smooth, fluffy emission rather than a bunch of point sources. And if you did that, you actually
question in the Q&A. What is?
Yeah, sorry.
I think I interpret this as what typically is the resolution in radio astronomy.
So typical resolution in radio astronomy, instantaneous for a single channel like this, you're looking at a few hundred to 1,000 to 1. But if you were, so what you can do is you can collapse across frequency and make a high dynamic range image. So your dynamic resolution in that can be very, 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 very high. So that can be a few million to 1. Does that answer your question? Feel free to ask a follow-up if needed. So you can end up with something like this, where your the reconstruction that you have made mimics what's actually in the sky. So this is the kind of stuff that you can typically do with radio interferometry. So if you, for example, some of the stuff that Nicole showed, and that's very easily transportable here, is that we both use complex array data. It's easily transposable from one to the other. Images that Nicole showed can very trivially be transposed to images here. We have all the tools and tools for it. We can also, of course, deal with the comma separated or any other kind of table data. So that can be read in, and we can make images of. So it'll be very interesting to try. One of the other things I wanted to ask Nicole is that if you know your sampling function, so you also know what kind of imprint that you get from the sparse sampling itself, right? Where you've just taken an FFT, but if you had replaced all the amplitudes by 1, and you just took an FFT to see the sampling, the kind sort of like the PSF that I showed you, what would that look like, Nicole?
It would just be a point in the center.
Yeah.
because that's how we purposely sample our data, so that, and there's different kinds of approximations. So, we're trying to collapse our image down into, some discretized, so we have an object in real space, where it's continuous, and we're sampling our data in K-space. with the assumption that we can discretize that actual object into something that is a finite image with a finite resolution. And so it's kind of a funny thing, like, as in radio astronomy, the actual K-space that we could sample would be infinitely large, or to represent the continuous object, if we were really trying to get to, infinitely high resolution. And so we have to make an assumption about the way the magnetization behaves when we're sampling it. And we call it a strong voxel approximation, that if we sample, enough of our K-space data far enough out to get a resolution that is high enough to not have us dealing with Gibbs ringing and things like that, then, the point spread function for that sampling will just be 1, right? It'll be 0 everywhere else with a 1 right in the center.
Accepting,
we don't have, like, the blurring is the extent of the voxel or the pixel that we're looking at. So when I did that undersampling, then our point spread function is actually 2 points. They're 1s with 0s all around them, where the 2 points are exactly half of a field of view away from one another, which leads to that aliasing artifact, where it's a very discrete, coherent aliasing, where we may have to undo that aliasing, but it's something where it's extremely aliasing that you're talking about is, the convolution with that very strange looking point spread function. Like, we can collect our data so that we have things like that too, and there may be reasons to do that. And the reason I didn't present that is because it's way more complicated, but it does come closer to the situation in radio astronomy, where you're not collecting nicely rasterized points in data space, which we can always do that. So usually we do.
No, we can't.
Yes, exactly. That's one huge difference. But most of our research applications now do involve collecting, we call it non-Cartesian data. It's data points that don't lie on that nicely sampled Cartesian grid. So we have to use things like the non-uniform Fourier transform when we're reconstructing our images as well.
So one of the reasons why I couldn't just simply do an FFT like the one that you had was because I don't have a regularized grid. Yeah. So like Steve points out, there is an FFT. There is a proposal to actually build an FFT-like array, so like a regularized grid-based telescope. So that's sort of mimicking MRI.
It's funny. So you're coming back in that direction, and we're definitely going away from that direction. And just to get away from an MRI only conversation. So in CT data, we don't collect at all data along a nice rasterized data space. We collect sinogram space. So basically, it's like the Fourier transform of data that's collected in like a star pattern, as basically you're swinging the entire X-ray emitter and detector around the body and collecting projections through the body, it's a very different way of doing it. And CT and MRI. Oh, I'm sorry.
It's helical.
It's helical, which it's even worse, exactly. Than
right. I mean, it's even worse. And when you're sampling through it, you're sampling in time space and data space, and then having to adjust for the fact that you're not straight on a Cartesian coordinate system. So you're looking at, essentially a spiral reconstruction kind of thing. And, that was one of the questions I was going to have for Nicole was, what about using polar coordinates and polar acquisition and polar reconstruction?
We do all the time.
That's another, that could be another hour discussion.
It's way more than that, which is why I kept it simple to actually the case that most of our clinical exams run on. And I think that's where the primary differences start between our fields. So we can choose exactly which points we collect. If we have an object that's stationary, we just scan forever and collect super high resolution. So our resolution isn't infinite. To go back, I think, to something that Sanjay was saying, we're limited by diffusion, where if our water molecules go too far away while we're collecting our data, then we can't localize them anymore. But that's kind of our resolution limit. We have ways of getting around that too, but it's a completely opposite spectrum of what you guys are thinking about.
Well, we're also driven by what's clinically useful, and in terms of how long does it take us to acquire the data, and what data is actually useful. I'm not necessarily interested in something that's a millimeter in size. I'm interested in seeing a tumor that's more like a centimeter in size. And then that's, useful to the diagnosis. So there's a lot of trade-offs that happen in the practical world, but you guys on the radio astronomy side, I think you're interested in anything that gives you a signal.
Yes, we are interested in large scale. We are interested in the large scale emission and what it is doing at very, very, very small scale as well. And that's why we build the kind of interferometers we do. One question I have about the data collection. We collect a lot of metadata from the receivers themselves, so that post data collection, we can do some calibration on it and take out the instrumental effects. For you guys, the data comes from a machine built by somebody who's making money and therefore don't tell you the format. Is there any possibility of getting that metadata from the receivers that you have used for example, MRI? The thing I have in mind is the K-space depends upon where knowing the location of the receiver very precisely. What is the location? And that must have some error on it and moving around. It also depends, it's a near field, so it'll depend upon its sensitivity pattern, what we call the primary beam, but all such sensors, your sensors have a primary beam. That information might be quite useful. We are able to derive, we have algorithms which are able to derive part of that information from the data itself. So that may be possible from your data, but do you get that metadata information, or is there any possibility of getting it?
Yeah, so I think it's useful to think about it in a different way, where we do use separate receivers to collect the data, but we can use our data to characterize those receivers almost perfectly. And so actually, like the data that I showed you was exactly collected at the MRI scanner. So I think where things start to get tricky is that if the magnetic field isn't perfectly homogeneous, like all your Fourier transform is trying to do is separate your time domain into your frequency domain. And so it doesn't understand if there's an inhomogeneity in the magnetic field, which would cause different frequencies to look like other frequencies and then place some signals in the wrong spot, right? And so that's where we do have to do corrections when it comes to field inhomogeneity, but we characterize all of that on our own scanners and build that in. It's nicer when the vendors do that themselves, but if they do that, then none of our research sequences would work. And so in order for us to be able to do the kind of crazy things, so we only use the vendor provided software to a certain extent. Like when we actually, just crack open, the hood and say, we don't want to collect it this way. We're going to collect our own data in our own ways, do our own corrections, do our own calibrations. And so we do that all on our own. And there's faster and slower ways to do it. There's groups that are better or worse, but we can completely characterize our system to be able to do that.
Sorry, I have a question. So you should put a single coil. And my other question is, if you had like in heat sampling and you have different coils, then your effective image is an overlap of these coils, right?
Yep.
So then you do have some sort of a sampling function, which is a combination of multiple detectors the moment you have multiple detectors, right?
Yes. And we use that information for our most common image reconstruction techniques. These are known as parallel imaging, where you use the spatial information that is inherent in having multiple non-completely overlapping receiver coils in order to localize the signal and resolve those aliasing artifacts. And it's really straightforward, actually. Like this is the next demo. The next hour-long demo would be how we use receiver coils to do exactly that. Yeah, but that's precisely what we do. But we have
so there's some more questions for you, I think.
Oh,
yeah. So somebody's asking, what's the impact of sample motion during scanning?
That's a great question. So it depends on where in the Fourier space that motion is occurring. If we have collected most of our K-space, we've gone through the center, which is the bulk of the contrast, and we're just looking for resolution on one of the far ends of K-space. Then we may see what we call light ghosting artifacts, where you can see the object and then kind of like little replicas up and down in the direction of that data sampling, where you can imagine that some of our Fourier data was collected when the object is in one position, and then some of it was collected when the object's in a different position. And so the result of that is just this ghosting. But it's Fourier data. So any errors that occur at any point in our data collection have impact over the entire image. So it's exactly the same issues that you have in radio astronomy, that every point in the image contributes to every point in the data that you collect, and vice versa. Any errors in any of the data that you collect will contribute to errors in the entire image. Yeah, so there's a comment about compressed sensing. So compressed sensing is becoming more and more common in MRI. So the idea of compressed sensing is that you have a lot of information about the features that your medical image should have. Like, you know, it should be kind of smooth, you know, that, you know, there shouldn't be big discontinuities generally in large parts of the image. And so you can use that to enforce certain kinds of sparsity on your images. And so you're looking for, you do an iterative solution where you're trying to find an image that is both consistent with the data that you collected and also has these features that you think your image should have. And I think that those sorts of techniques work really well when your images themselves are sparse or transform sparse. You know the space in which they should be sparse. Those work to a certain degree in MRI, but often this is the trick with compressed sensing type techniques, that, you know, the ultimate user, you know, the consumer of the images is a radiologist, and anything that looks artificial, looks overly smoothed, it looks blurry, or like, for us, resolution is key, right? Resolution and SNR, you need those two things, and then the contrast to be able to tell something that's healthy from not healthy. And so if you're going to get a blurry image, the radiologist is going to say, give me noise, give me less contrast, I don't want blur. And so it's been, the compressed sensing techniques are moving into the clinic, but they're slower than things like parallel imaging, where you're using receiver coils. It's basically a deterministic reconstruction. You know, you use the data in a certain way and you get it done, as opposed to a compressed sensing reconstruction where you're going to have an image where you're kind of generating data based on assumptions. And sometimes if you assume an image should be smooth, it will be smooth, even if it shouldn't actually be smooth, you know, smoothing over a tumor or something else that you wanted to see. And so it's been taking some time. But I think actually, like, in radio astronomy, compressed sensing is like, those are the kinds of images where it seems like it would work really well.
Yeah, that being said, there's
sensing in radio astronomy, I'll just have a quick comment that whatever Prashant showed is actually formally can be shown to be a compressive sensing kind of algorithm. So while we never call it compressive sensing ideas have been in use in radio astronomy for a very long while.
To be fair, it's the same in medical imaging. There have been people who've been doing, you know, sparse recovery techniques for a very long time. It just hasn't been called compressed sensing. It was, you know, about 15 years ago that term came into play. And I think it's just, you know, as soon as computers are faster, then you can do all sorts of crazy iterative things that we weren't able to do more routinely before. And so that's when it became very popular.
Let's open it up to the general audience. If anyone has any questions they want to ask or comments to make before we wrap up.
Yeah, so I just want to comment that I think it's exactly the kinds of conversations like this that I'm really looking forward to continuing at the in-person meeting, because I feel like there's so many things that are much clearer to ask in context, or to see those relationships in context. And when we actually sit down and we're like, here's how I do it, here are my constraints, it makes it a lot easier for me to understand, you know, where our similarities are. So I think just this conversation has been really awesome as a segue into that in-person time. And I'm really looking forward to that.
Well, thanks again, everyone. We look forward to your communications between now and the workshop, and hope to see you all at the workshop. And please invite all your colleagues and friends to join as well.